Okay. All right. There we go. Okay. Excuse me. So we're going to get back into things right now with some Unit 3 review for Physics 2. I'm going to start this off with some electrical magnetic waves. This is section number 18. As always, this is a review for me. I'm just doing this to document my studies so I can go back later and hopefully have a good time reviewing it some more. So this is part 18. This is the first section of Unit 3, part 18. Electromagnetic waves. EM waves. Okay, in this section we'll look at Maxwell's equations. The electromagnetic wave equation, the speed of light. The electromagnetic waves, of course traveling waves, intensity with the pointing vector, the polarization of light, Laplace's law, and the nature of light, which goes into rays, photons, and waves. So firstly we have Maxwell's equations. These, we have no charge, no current. In the no charge side, we have Q is equal to 0. So the line integral of E dot dA is equal to 0. And the line integral of B dot dA is also equal to 0. Meanwhile, we also have no current. I is equal to 0. So the line integral of E dot ds is equal to negative d phi b over dt, where phi b is the magnetic flux. And we would also have the line integral of b dot ds is equal to mu 0, or the permittivity of free space, epsilon 0, d of phi e over dt, where phi e is going to be your electric flux, your electric wave flux, yeah. So with Maxwell's equations, a varying E rises to a spatial change in B. with Faraday's equations. With some simple math to get a EM wave, if we start with Faraday's law, we can take some partial derivatives and the space derivatives to switch the orders, and eventually we're going to find that the velocity of a wave is going to equal to 1 over the square root of mu 0 epsilon 0. Now there's a relationship between the E wave and the B wave. In this relationship, we can find that E, which is our electric field, is equal to E0 cosine of 2 pi over lambda x minus 1 over root mu 0 epsilon 0 t. Which will equal to E0 cosine of 2 pi over lambda x minus ct, where c is the speed of light. C is equal to the speed of light, which is equal to 3 times 10 to the 8th meters per second. The velocity. And then we have this thing, this S. And S is equal to the pointing vector. So S, or the pointing vector, is equal to 1 over mu sub 0 E cross B, where E is the electric field and B the magnetic field. We also know that the electric field is 90 degrees off magnetic field. Now, some harmonic traveling waves. In harmonic traveling waves, we know that y sub t is equal to y sine 2 pi over lambda x minus 2 pi over t sine of 2 pi over lambda x minus lambda over t t. Now it should be noted that the second t I said in there, it's 2 pi t multiplied by t, where the t that's being multiplied by is time, and the t that the 2 pi is over is the period. We know that the velocity, the phase velocity, is equal to lambda over period, where lambda is the wavelength, which is equal to lambda frequency. So we can say that y sub t is equal to y sine of 2 pi over lambda x minus velocity t max. And of course we also know that k k is equal to 2 pi over lambda. And we know that omega is equal to 2 pi frequency. And we know that V is equal to lambda F, which is lambda frequency, which is equal to omega over K. And then so we can say that Y is also equal to Y sub m sine of kx minus omega t, which is equal to Y sub m sine of k x minus a velocity t. And that velocity is that t is time. It's lowercase t. Okay. Now, we also can say that in a traveling sine wave, y sub t is equal to y sine of 2 pi over lambda x minus velocity t plus phi sub 0 max. A point with a specific phase moves to the right at speed velocity, or speed v. So now we're going to look at intensity. Intensity is defined as the average rate of energy transfer which is going to be power P per area. So it's through a surface. So we can say that intensity is equal to power over area. And the units are the watt per meter squared. So we also have this intensity. It's a Poynting vector. S is equal to 1 over mu 0 E cross B, the Poynting vector. So what does this tell us? Well, I, which is the intensity, is equal to S, which is the Poynting vector, which is equal to 1 over mu sub 0 EB. Technically, in that equation, there is a line over EB, which is equal to 1 over 2 mu 0 E sub m B sub m. So you can say that I, because E sub m is equal to C B sub m, where c is the speed of light, you can say that I is equal to E squared sub m over 2 mu 0 c, where c is the speed of light, which is equal to c b squared sub m over 2 mu 0 sub 0, where mu is the permittivity of c space, E is the electric field, c is the speed of light, and b is the magnetic field, I is intensity, and S is the Poynting vector. which of course is equal to intensity, so this is all equal to S. Now, isotropic flux point source. The net power transmitted through a closed surface is the power emitted by all sources inside that surface. Making use of symmetry, as with Gauss's law, if a spherical surface of radius r is imagined centered on a point source, the intensity will be the same at any point on the surface. So we can say that I is equal to P over A, which is equal to P over 4 pi, or squared. The power emitted is P. Area is equal to A, which is equal to 4 pi r squared. Yeah. Now, electromagnetic pressure. So P is equal, little p is equal to the radiation pressure. And this, of course, is equal to the equation epsilon 0 E squared m over 2, where E is equal to the electric field. An electromagnetic wave incident on a surface carries energy, the Poynting vector, and momentum. Now, the polarization of light. At any instant, the electric field in a wave points along a particular axis up or down. If this axis is consistent in time, then the wave is linearly polarized. A polarizer allows through only the electric field component aligned along the polarizing direction, where, according to Malice's law, I transmitted is equal to I incident cosine squared of theta, where theta is the difference in the angle between the incident E field and the polarizer setting. But now, light can become polarized by reflection. Any light wave can be decomposed into the polarization parallel of a perpendicular to a plane. In reflection, a meaningful plane is the plane of an incident containing the incident wave vector and the reflected wave vector. Reflection of light polarized into the plane goes to 0 when theta incident plus theta refracted is equal to 90 degrees, which can also be stated as tan theta, INC, is equal to N2 over N1. In summary, the analysis of Maxwell's equation shows that the electromagnetic field can travel as a wave through empty space at a velocity is equal to 1 over epsilon mu 0, which is equal to c, the speed of light. The electric and magnetic fields are perpendicular to each other in the propagation direction, where s is the Poynting vector, is equal to E cross B over mu theta, which is the instantaneous intensity. Electromagnetic waves carry momentum and exert pressure. Linearly polarized light has the electric field along only one axis. Excuse me. I'm about to wrap up things tonight. If you tuned in, thank you for tuning in. Have a good evening. I should be back on here sometime tomorrow morning to finish up Unit 3. In that time tomorrow morning, I plan to cover wave interference, diffraction, or relativity, photons in wave-particle duality, and the wave function and probability. That should be early tomorrow morning, and I'm planning on getting it all done by noon. And then afternoon, I'm going to take a break for lunch, and I'm going to get back on here and work questions till about I'd say around between 5 and 6 is when that'll be over, where I'll take a short break for dinner, and I'll be back on between 9 and 10 to work some more questions. So that's where I'm standing right now. Yeah.